The plan for today is that I finish the story about structure theory of algebraic groups in characteristic P, which then serves as a motivation for the structure theory of quantum groups at roots of unity that we are going to discuss next. Yeah, this will be Jay will do that. We care in this lecture about distribution algebras. And the last thing that we discussed last time was about Frobenius homomorphism. So let me do a brief reminder. We have a characteristic P field F, and then for a scheme X over F, we can consider its Frobenius morphism, which on the functions just gives P's power. And if your scheme was a group scheme, then this is a group homomorphism. And here is a very concrete example for GLM. And last time we finished by discussing what happens, what this thing does on distribution algebras. So today, we are going to start by talking about Frobenius kernels. And that's, I think, section 3.3. So what's going on is that Frobenius, which is an algebraic group homomorphism from G to G1, is an epimorphism. But it's not an isomorphism. It has kernel. And this may sound surprising because Frobenius is clearly an injective map. So on the level of points, the kernel is trivial. It's just the unit element. But as a group scheme, it is not trivial. And more generally, so definition, the R's Frobenius kernel G sub R is, the kernel of Frobenius to power R, which goes to G twisted by R. And it's a non-reduced group scheme. With a single point, which is 1. So let's try to consider an example of this. Let's say it's example number 1. So let's take the additive group. And let's describe the Frobenius kernels. So the algebra of functions on this group is just polynomials in the variable t. And what Frobenius to the R does, well, it sends the variable t to power p to R. And therefore, G sub R is the spectrum of, well, preimage of the maximal ideal of 0 under this map. Of course, this preimage is generated by this element. So it's going to be the spectrum of f of t modular t to power p to r, and of course that's clearly a non-trivial algebra. Okay, so that's a non-trivial scheme. How is the scheme a group? Well, we notice that for the coproduct delta, which goes from f of t to f of t times squared, we have delta of t to p to power r. It's going to be t to p to power r times 1 plus 1 t to power p to r. Okay, so the ideal generated by t to power p to r is a bialgebra ideal, and for the similar price is also a Hopf ideal. So the quotient that we consider is a Hopf quotient of polynomials in one variable, which is algebra of functions on the initial group. So that's how the Frobenius kernel is a group scheme. And then we can also consider the distribution algebra. So distribution algebra, again in the same example. What is this? So we are talking, so before the distribution algebra was constructed as follows. We took the dual of the algebra of functions and inside considered some finite part. Now we no longer need to consider the finite part because everything is finite dimension. So distribution algebra in this case is just the full dual, and in fact it sits inside of distribution algebra of G, because GR, it just sits in it's a subgroup scheme. How does this embedding work? What is this subalgebra? Well, so last time we defined gamma sub I inside of this G by gamma sub I of t to power n is Kronecker delta of I and n. And these elements form bases in this G. Then you can easily see from the description of the algebra of functions on GR, which is this quotient, that the distribution algebra of G sub R is a span over F of the first P to R elements in the basis gamma. And that's a subalgebra. Questions, please.
Maybe just something, Ivan, I think you mentioned last week, is the fact that the Frobenius map is locally around the origin, not an isomorphism, because the Jacobian is 0, I mean, the map of tangent space is 0, just to, yeah.
That's right.
So, yeah.
Not only the, well, I mean, that's right. So the differential is just 0. And which we can clearly see in this example and every other example. Thank you. More questions? All right. So a brief remark about the gel case. So we still have that f sub gr is a Hopf quotient of G of Fg, and therefore the distribution algebra is a Hopf subalgebra of distributions of G. Exercise is to see what happens for the multiplicative group. So G is GM. Then let's see, f of gr is a quotient of the group algebra by the ideal generated by t to power pr minus 1. And distribution algebra of our Frobenius kernel is spanned by the elements beta 0 to beta pr minus 1. Where beta I was a basis element defined as follows. So beta I t2 minus 1 to power n is Kronecker delta. Okay. So these are baby examples. What we care about is the case when our group is semi-simple, and for simplicity, we also impose the condition that it's simply connected. So for G semi-simple and simply connected, we have the following proposition. So first of all, we can describe the distribution algebra of the Frobenius kernel as a subalgebra in the ambient distribution algebra. So last time we have described, let me scroll up, we have described a basis in the distribution algebra of a semi-simple group. And the basis looks like so. So what's the meaning of this notation? E minus alpha is a negative root vector. And these guys are basis elements in the additive subgroup which corresponds to this root, okay? They are divided powers. Then these guys are a basis in the distribution algebra of a multiplicative subgroup which corresponds to simple root beta. And then similarly, we have these guys for positive roots. And you can make an educated guess of what should be the basis for distribution algebra of the Frobenius kernel. You just put constraint on these exponents, k alpha, m beta, and n alpha, similarly to what we've seen in our example and our exercise. Let me write this down. So as a subalgebra of dist G, dist of G sub r is spanned by the following elements. So it's going to be product over alpha in phi plus. Let me write this as divided power e minus alpha to divided power k alpha, product over beta in pi, beta check, choose m beta, and then product over alpha in phi plus, e alpha to power n alpha. So that's the first part. And then recall that the universal enveloping algebra U of G naturally maps to the distribution algebra of the group. Now, inside here, I have a subalgebra, which is dist 1 of G. And here I have a quotient, which is this reduced universal enveloping algebra discussed in the beginning of the previous lecture. And turns out that the homomorphism upstairs factors through an isomorphism downstairs. And I forgot something, so I forgot inequality on exponents in the first part. So all of them should be less than p to power r. Questions, please?
Ivan, when you write beta check, do you mean like the differential of beta check evaluated at 1? Is that you mean the actual?
Yes.
Okay.
Well, beta check is an element of Cartan subalgebra, and which maps to distribution algebra. All right, there is not much of a proof, so let me put it this way. So, not really a proof. So one is for the same price as theorem above. The theorem that I referred to before stating the proposition. And then for the second part, you can argue in several different ways, because the easiest one is like this. So this homomorphism sends E alpha, well, E plus minus alpha viewed as an element of a Lie algebra to E plus minus alpha in the distribution algebra. It also sends beta check to beta check. And then, well, you can see that subalgebra in this G generated by these elements is precisely this G1. The point being that when all of your exponents here are less than p, then you don't really need to take any divided powers formally. You can just take the corresponding power and divide, because everything you divide with is non-zero, okay? Then you can see that U of G, well, you can see that E alpha to power p well, I should write e plus minus alpha to power p, and beta check to power p minus beta check equal to 0 in the distribution algebra. We just give 0 functions on the group. That's easy to check. And so u of g to dist 1g factors through u0g surjection into dist 1. And you can say, for example, that on basis elements is the identity, or you can say that dimensions are the same. Well, let me say the latter. So dimensions are both equal to p to dimension of g. So this surjection is actually an isomorphism. And this finishes the proof. Questions, please.
I have a question. What is the difference between dist 1g and dist g1?
One of them is a typo.
Okay.
More questions? So I just want to emphasize that this sort of isomorphism is important for our quantum purposes. We work on characteristic 0, so we will only see one Frobenius curve, a so-called small quantum group. The others don't make sense. Okay. Now I want to give a brief account of a connection between rational representations of G versus modules over the distribution algebra. I'm not going to give proofs to save time. I will put some proofs and hints of proofs in the notes. So what do we care about here? We care about the following two categories. We have the category of finite dimensional rational representations. On the other hand, we care about the category of finite dimensional modules over the distribution algebra. And more importantly, we care about connection between the two. We'll see that this connection is very close. In particular, when we are dealing with semi-simple and simply connected group, these two categories are naturally the same. But first, I need to describe an action of dist G on a rational representation. So there is such an H election. Let me explain how it looks like. So let me pick a rational representation. Doesn't need to be finite dimensional. Let's call it 10. What are rational representations in algebraic terms? These are comodules over f of g, the algebra of functions. So what does it mean to be a comodule? It means that I have a map, the action map from a module to fg times this module. And now on M, I want to describe the structure of a module over this G, for which I will use this map. So what am I going to do? Well, distributions, they eat functions and spit scalars. So I can just take my distribution, I can feed the functions here to the distribution, and I will get an element of M. So we define for a distribution D, define D applied to M as follows. So maybe let me write alpha for the map instead of A. So let's write alpha of M as the sum over I, AI times MI. No, alpha is better. Sorry, alpha looks like a D. Let me write it. And then D applied to M is the sum over I, D of AI times MI. And just by the very definition, this factor here is a scalar. So this makes sense. Questions? If no questions, you get an exercise which is unpleasant, but is very good for your mathematical health. Which is the following, is to show that this equips M with dist of G module structure. And a hint, revisit definition of the product. On dist of G. Okay, so from a rational representation, I can get a module over distribution algebra. Let's look at an example. Example is going to be for the additive group. So what do we get here? A representation with an algebraic group homomorphism. So every algebraic group homomorphism from GA to GLM has the form T goes to the identity plus the sum over I I big or equals than 1 I times Ti. And this needs to be a finite sum. Okay. Now, if I have a representation, how does my distribution algebra act? Well, it's easy to see. That gamma I acts by what? Does anybody in the audience, preferably without PhD degree, want to answer? So who was gamma I? Gamma I was a characteristic function of the element T to power I.
Is it not just AI?
Okay, Gurbir wasn't qualified, but answered anyway. Thanks, Gurbir. It's AI. And it's what you see when you just look at the definition of the action map. And then relations in this G, and the relations look like gamma I, gamma J is I plus J. Choose I times gamma I plus J are just equivalent to say that this map I big or equals than 1, AITI, is a group homomorphism. So it looks like we see that modules over this G is exactly the same thing as rational representations. Is this so? Is the same thing as, well, finite dimensional, this G module. So true or false? So is this here a true statement or a false statement? Does anybody have suggestions?
Or maybe I am I allowed to say
Well,
something? I mean, it's
Maybe
cheating
you're
because I know the end.
qualified.
Okay, I'm not going to say anything.
So it looks like, you know, I take this G module, which is a bunch of operators, gamma I, satisfies these identities. And then I can use this formula to cook a representation of G sub A. This is a true statement.
Maybe you could ask a question and replace this G with the Lie algebra. You could ask
Well,
a
the
similar thing
algebra,
for the
it's
Lie
more or
algebra.
less clear that this is not going to give the right answer. This G is certainly a better answer. Guys, anybody? All right. So here is the answer. The answer is no. You see, if you can pick operators satisfying this, infinitely many of which are non-zero. Okay? That's actually possible. So if you want the equality, then you need to add something where only finitely many gamma I act by non-zero operators. That's an essential restriction, and you can actually compare with what happens in characteristic zero. Characteristic zero, you don't have distribution, you just have a Lie algebra. But if you just start with representation of a Lie algebra, what you get will be representation of a Lie group, not of algebraic group. And something more or less similar happens also in the case of characteristic P. Questions, please. Okay. I feel a little bit like, you know, a lead actor in a movie about ghosts. And this movie gets more and more scary.
Can you give us an example where infinitely many of these would be non-zero?
You can get a two-dimensional example.
Can you show us?
Exercise. Look, I'm an old guy. And I'm lazy. So how about example of the following way, of the following form. So module M is F2, and all gamma i's act, well, gamma i's with I bigger than 0, act as multiples of 0, 1, 0, 0. So you want to work out this condition. And you can see that it actually doesn't imply that only finitely many of these elements act S act as 0. Okay, that's an easy check. Okay, but it's good to know that living people are still here. All right. So let me give you some collection of results, and then I will finish. So first of all, let's talk about what happens when G is GM, the multiplicative group. And turns out that the structure of rational representations for this group is the same as in characteristic 0. So proposition is that every rational representation is isomorphic to the direct sum of one-dimensional representations and every one-dimensional representation is given by t goes to t to power I, where I is an integer. Okay. So let's see what's going on for the distribution algebra. So what is this? It's a span over F of the elements beta I is bigger or equal than 0, where beta I should be thought of as beta 1 choose I. Okay. In particular, the relations in this algebra, maybe it's more transparent if I talk about the distribution algebra over the integers, are those of binomial coefficients. You can make it precise, which I don't want to do. So using this, what I can do, well, I can plug everything into a binomial coefficient. In particular, I can plug a periodic number. So for x, a periodic integer, I have homomorphism from dist gz to the periodic integer, which takes beta I and sends it to x chose I. Okay. Now, what I can get from this is a homomorphism from this G to Fp. And Fp, of course, sits inside of F. So, before, for the algebraic group, one-dimensional representations were indexed by the integers. Now, I have a one-dimensional representation for every periodic integer. And there is an obvious correspondence. If you differentiate this one, this representation, if you consider the representation of distribution algebra induced by this, you will get, well, maybe I is bad here, let me write J. You will get the representation corresponding to J viewed as a periodic number. And it turns out that other than this, there is no difference between the two settings. So every finite dimensional dist G module is isomorphic to the direct sum of one dimensions. And every one-dimensional representation comes from an element of the p-adics as above. Okay. So in particular, we again see that not every representation of the distribution algebra comes from a representation of the corresponding algebraic group. Questions, please. All right, that's the only thing that I want to do in the remainder of my talk is to state the following theorem, and I will give a sketch of proof in the notes. You can guess what the setting will be. When G is semi-simple and simply connected, then our factor from finite dimensional rational representations of G to modules over this G is an equivalence. So in this case, every finite dimensional representation of this G comes from a rational representation of the group. So that's a nice result. And in particular, if we care about semi-simple and simply connected groups, then we can fully replace our algebraic group with this algebra, which is what we are going to do for quantum groups, at least for time being. And maybe I should add that you can extend this result to connected reductive groups. You just need to put some condition on weights, because the second proposition will only tell you that the Cartan part will act by some p-adics. You actually need to impose a condition that these p-adics are integers, and this collection should belong to the character lattice of your group. All right, this is the end of this talk of myself, and let's make a break. Jay will speak after the break. Meanwhile, are there questions?
Maybe you, sorry, no, go on.
Oh, thanks. So is it always fully faithful, or?
It's fully faithful under reasonable assumptions. Like, I think if you deal with actual algebraic groups, it's going to be fully faithful.
Great. Okay, thanks.
Elijah?
Yeah, I guess maybe this is sort of related, but how does this, I mean, in the connection between this and the previous section where you're thinking about modules for disk G1, does this equivalence play well with Frobenius twist?
Yeah.
Okay.
Well, I mean, this function is compatible with forbiddeness, and you know, under very general, again, under very general assumptions, if not always. So if you have a group homomorphism, then it gives you natural transformation of functors. How about this? Okay, guys, let me resume the recording.
Okay, great. So yes, so now we're going to do quantum groups again after a detour through algebraic groups. So like I mentioned right at the beginning a bit ago, we're going to look at kind of two forms of the quantum group, which one is given by Katz-DiConcini and the other one is given by Lustix. So we'll start with the DiConcini-Katz form. Of the quantum group. Okay, so just some notation, right? So V is an indeterminate over C. So V is, I want to think of it as an indeterminate, but really, right, this is just playing the role of my Q from before. So there was some concerns that my Ks and my Rs look the same. So I'm going to try and draw my Ks with a curl to distinguish them from my Rs. So I'll let K be the field of fractions of the Laurent polynomial ring. Right, so G complex semi-simple Lie algebra. Right, and then we've got simple and positive roots. And remember there's this number, so we have this bilinear form and we scale it so that all short roots have length 2. And then we get this number, which is in 1, 2, 3. Right, so it's been a while, so let's just recall a few things. So, right, so as in Janssen, I'm going to let UK this is going to be the K algebra with generators E alpha, F alpha, K alpha plus minus 1 for alpha and pi, and relations, right? So I'm not going to list them all, but let's just kind of remember a few. So, right, so these K alphas are invertible in the commute. So if I conjugate by a K alpha, then I get V alpha beta E beta, and the same for, but with signs. And then I have these commutation relations where delta alpha beta is just the Kronecker delta. Okay, so there are these kind of standard relations, and then there's the quantum set relations, which I'm not going to worry about. Okay, so I use this notation here. So let's just recall that for any A and Z, okay, we're going to have that, right, this K alpha A, this is K alpha V alpha to the A minus K alpha inverse V alpha to the minus A all over V alpha to the V alpha inverse, where V alpha is V to the D alpha. So let me just mention this now, because it'll come up later. But there's a reasonable amount of flexibility when it comes, I mean, this power here, this D alpha, I mean, we chose it to be this kind of very small number, but actually in reality, there's a lot of flexibility about how we could choose these powers and what could go there. And that's actually going to play a role later when we consider Lustig's quantum Frobenius. So just bear in mind that there's some flexibility there in this setup. Okay, so this Deacon-G-Cat form. Okay, so the Deacon-Cheney-Katz form of UK is the R subalgebra UR generated by, so I want the E alphas, the F alphas, the K alpha plus minuses, and what I'm going to throw in as well are these terms. Okay, so obviously I don't have, I have to kind of deal with the fact that I want something that's like an integral form. So I don't want to divide. So I'm just including a generator which basically contains this, this element. Okay. Okay, so maybe I'll just say this.
And
so,
maybe a little remark. So if you are willing to invert this V alpha minus V alpha inverse, then you don't need to do that.
Yes, exactly. So another option would be to, in my ring R, I could just invert that that denominator, and that would also be an option. Okay, so just a reminder, Janssen, like you could, you know, he can work more generally with lattices lying between the root lattice and the weight lattice to set up his quantum group. But I'm just going to work with the simply connected version, so I'm always just going to assume that I'm working with the root lattice. And I also wanted to make one more remark. So kind of implicitly, we've actually already basically seen this algebra. So UR appears implicitly in lemma 5.12. So he basically shows that some lattice is a module for this algebra. Okay, and this is really kind of an R form of the algebra, right? So we really have the UK, right? If I just extend scalars over R, this is, I really get back the algebra, then I'm interested in OK. Okay, so now what we can do is specialize at a root of unity, which is what we're kind of interested in. So if we take epsilon, well, any non-zero scalar, let's just let C epsilon be the R module with V acting via scalar multiplication with epsilon for all C and C. Okay, then we define U epsilon just to be the specialization. Okay, so this is just a C algebra where my parameter now is considered as a root of unity. Okay, so maybe the first thing that we could do is try and take this parameter to be very small. And so what's kind of the smallest thing we could take? Well, we could try and take plus or minus 1. Okay, so so if we take epsilon equal to plus or minus 1, then for each alpha in pi, okay, we have k alpha is in the center of this algebra, and k alpha squared is equal to 1. So this is really just an immediate consequence of the relations. Right, so moreover, well, if we just set h alpha equal to this element k alpha 0, then that last commutator relation just becomes, can be written like this. Okay, so this looks really close to the Lie algebra. And actually, we get the following. So we have, so if I take the specialization at 1 and I mod out by this subalgebra, then this is going to be isomorphic to the universal enveloping algebra of the Lie algebra. So let's just make a remark about why this is the case for, let's just look at the case of SL2. So let's drop the subscripts. So we just need to see that the relative relations are satisfied. So I'm going to drop the alphas from the subscripts. So just write H, E, and F. So to see that this relation holds, we can apply the following formulae, which are not difficult to deduce. So actually, these hold in the generic algebra. Okay. Well, this is just the standard thing that if I pass an E over one of these KAs, then I pick up a 2. Okay, in the SL2 case. And similarly for HF minus FH is minus 2F. And obviously the only other interesting relation that you want to know that holds is exactly this one here, okay? Okay, so we're going to be interested in the center of this specialized algebra. Yeah.
Let me try to make a remark. So first of all, the initial relations. Okay. So it's right. It's already written. So k alpha squared is equal to 1, then k alpha central. And what we'll see is kind of this that we need to model this relation is the same kind of annoyance as what we had when we needed to restrict to type 1 representations. And this annoyance actually is persistent. So it appears in many other places. So for many results, you will, instead of considering the full specialization, you will need to model it by an ideal like such.
Well, that's a general property of annoyances. They tend to persist.
That's also true.
Okay, so we're going to be interested in the center of this algebra. So let's recall some formulas to make it easier to see what the center is going to be. So let's just recall the following formulae. So if we take the commutator of E alpha and F alpha to the S, it's going to be S alpha right, and then we can look at it the other way around. Okay, so this is true for all s greater than 0, and right, just a reminder as usual, right, a is v to the a minus v to the minus a all over v minus 1 for all a and z, and this a sub alpha, that's a where I specialize v to be v alpha. Okay, so actually let me just mention this now. So just for some notation, okay, so UR plus it's the subalgebra generated by the E alpha, and UR minus is the same generated by the F alphas, and UR0 is just generated by the K alpha plus minus ones and the K alpha zeros. Okay, and then we can just look at the images. So U epsilon plus minus or 0 images in U epsilon. So there's there's a remark that is made by Deacon Ginny Katz that you can, and it's also kind of pointed out by Janssen in his book, which I'll just kind of, I'm going to say this, and then if you want to know more, you should just ask Ivan, because he actually knows really how to prove this. So it's just to say that we know that the universal enveloping algebra has no zero divisors. So you have this generic algebra with a specialization that has no zero divisors. And the kind of remark is that there is a way to kind of prove that the generic algebra over R actually also has no zero divisors. So
well, the generic algebra and actually all of it, well, essentially all of its specializations.
yeah.
Maybe after you massage them a little bit.
Okay, so let's start by looking at the center of
So maybe it's
this specialized universal enveloping algebra in the
it's worth pointing out that what we are after is seeing things similar to the corresponding setting characteristic P.
yes, yeah. So
Like
what we should see here now.
Go ahead.
No, sorry. Yeah. Okay. So what I just want to say, so we should expect now that the center of this algebra is should have quite a few elements. So we'll kind of remember, like in the characteristic or in the kind of away from a root of unity, we saw essentially that you have just the Harashchandra center generated by the quantum Casimir element, and we should expect more now. So the center should be larger in this specialized algebra. Is that okay? Is that,
yeah?
Do you want to say more? Okay. Okay. Okay, so we already saw, like, we already kind of know what happens when epsilon is plus or minus 1. So let's assume now that epsilon squared is not 1. Okay, so okay, so just kind of said this, but let's write it down. So so the center of UK is generated by this quantum Casimir element. And so obviously specializing just look at this as an element of our specialized algebra, gives an element of the center of our specialized algebra. Okay, so we know what happens when epsilon is not a root of unity. That's we get the same answer. It's just generated by the Casimir elements. So let's assume epsilon is a root of unity. So there's going to be an elf root of unity. And let's let L prime be the least positive integer satisfying so when I take the this term, then and I specialize it, I should get 0. Okay, it's an exercise. So just to check, it's not difficult that L prime is L over 2 if L is even, and it's L if L is odd. Okay, so just recall, so if G is SL2, then E to the L prime, F to the L prime, and K to the L prime are all elements in the center of the specialized algebra. Okay, so what is it? Plus or minus? Well, this is easy. So for the K, it's straight from the relations. The defining relations. Okay, so for EL prime and FL prime, actually what we want to use are these commutator relations that we wrote down here. And so you'll see why the L prime plays a role, because it's exactly going to make this term vanish. Okay, so in both cases. Okay, so for EL prime and FL prime, use the prior commutator relations and the defining property of L prime. Okay, so actually we can say more, but I'm not actually going to do more. The center is actually generated by C EL prime, FL prime. Okay, so this actually gives a full generating set. So remember in the algebraic group case, right? This Veldkamp's theorem. You have this P center and the Harish-Chandra center. So this is these terms here are kind of playing the role of the P center. So let's just so the algebra generated by is the analog of the P center. And that generated by C is the analog of the Harish-Chandra center. Okay, so essentially the same phenomena holds in general. So in the essence of time, I'm just going to assume that epsilon is a primitive Lth root of unity with L odd. So the L odd case is worked out by Di-Concini-Katz-Procesi, and there you are also kind of analogous statements when L is even, which are due to Beck. But I'm just going to look at the odd case. Okay, so
It
basically the first.
The even case presents some essential difficulties.
Yes, it's much more another reason why I don't want to do it, because it's harder.
So people traditionally look at odd case because traditionally there is an interest even in the case, even in more restrictive case, when the order is prime because of connection to representation P, connection to representation theory and characteristic P.
Okay, so maybe just the first thing to say is that the complete analogy of what we had before for SL2 holds in general. So all right, so these are central elements, and I don't have to use L prime because by my I'm just going to use, I just get L, okay, instead of L prime. Okay, so what we want now is kind of what should be the analog of the P center. So actually to make the definition, DCKP use the braid groups. Okay, so.
And DCKP is the Concini-Katz-Procesi.
Yes, yes, that is. I should just say Di-Concini-Katz-Procesi. That's less lazy. Let's see if I can. I got it. There we go. Okay. So let's take the braid group. Okay, so the action of B on this algebra UK, which was established in Calder's talks. So this stabilizes this subalgebra UR. Okay, so we get an action via the specialization of the braid group on this specialized algebra. Okay, and we define Z0 so this should be the smallest B invariant subalgebra containing the following elements. I need to make an assumption which I didn't make, forgot to make, but I'll make it in a minute. So I want this scalar that I'm using here to be non-zero. So I'm going to want this to be I'm going to want L to be greater than d alpha for alpha and pi. Okay, so this is Di-Concini-Katz-Procesi's analog of the p-center. Okay, so
well, actually, let's see. So we already require that epsilon is odd root of unity, and we assume that epsilon is different from 1. So any number is going to work everywhere outside type G2.
yes. Right, yeah, because I'm assuming my d
For
alphas
G2,
are the
we need to
yes.
additionally exclude third roots of unity.
Yes. So as long as I'm kind of not 3 in G2, then I'm okay. Okay, so we also kind of can construct. So we've already basically seen how to construct the Harishchandra center at the level of UK in the previous talks, and one can take that construction for the Harishchandra center and specialize it, just like we specialized the quantum Casimir element, to get another central subalgebra of U epsilon. So let's Z1 be the Harishchandra center. Be the Harishchandra center. Obtained from the center of UK. Okay. And so essentially what is shown by Di-Concini-Katz and Procesi is that the natural map so the natural product map is an isomorphism. Okay, so this is Veldkamp's theorem, okay, that we saw before. Okay, right, and so there's just one more thing to say about this form, and that is, well, I want to say two more things. Okay, so maybe I'll just say one more thing about this center. So they show, so that one has a covering of the open cell in corresponding algebraic group by spec of the center. So this is an unramified Galois covering of this of this open cell. So you can kind of think of this center as being functions on this open cell. And I think I don't want to say more about this unless Ivan wants to say more about this.
So, and the order of the degree of the covering is 2 to power rank.
Yes.
Yes, and that's another instance of the same annoyance that we discussed earlier. And actually, a good way to think about this, maybe just a little comment, is that in the old world of characteristic P, the P center was functions on G dual, on the B algebra, the dual of the B algebra. And this guy here, G0, is actually the dual Poisson B group. So there is also analogy here.
Right, and then there's just one more thing to be mentioned, is that the center carries a Poisson structure. So when we were looking in the case of algebraic groups, when you look at the Harishchandra center, you can think of that as the G invariance under of the center. So there's something analogous that can be said here as well, but the group you have to construct is an infinite dimensional group that arises from this Poisson structure. So I'm going to let Ivan say more about this, because I think you have more feeling for what about these Poisson structures than I do. So.
Right. So maybe the thing to be said is that if you have a non-commutative deformation of your algebra, then this deformation just gives you Poisson structure on the center. So the center doesn't need to deform to a central subalgebra, and so the failure of it to remain central is going to be included, is going to be described by a Poisson bracket. And so the Poisson structure on Z0 comes from there. So the Harishchandra center does deform to a center, Z0 does not. And one can actually write formulas on how this Poisson structure behaves, but I don't think we have time for this.
No. Could you say why the Poisson structure is important? Like, I mean, I know one shouldn't just ignore, if its structure's there, you shouldn't just ignore it, but like, why is it so useful?
Well, in this particular case, for example, one notable result of the Concini-Casson Procese was the following. So now that we have this P center, we can consider P central reductions. We can take a maximal ideal in Z0 and model it out from our algebra. And you can ask, what kind of algebras do we get? And the answer is still unknown, but it's known when two such algebras are isomorphic. And this isomorphism is essentially provided by an action of this infinite dimensional group. So that's, I think, the main result in that paper of the Concini-Casson Procese.
Okay. All right, so that's kind of all the I think we want to say about this Concini-Casson Procese form. So now we're going to move on to the Lustix form.
Wait, sir, before you go on, so just for the P center, is there some nice PBW basis for it?
Well, the P center, you can, yes. So, I mean, really, they basically, you can view it. So they give a triangular decomposition for the P center, and they also show that it's behaves like it's a polynomial ring over certain generators that they write down. So these, I didn't really get into it specifically, but these. So these generators, these Y alphas, you can using the braid group action, you can kind of construct more Y alphas for not necessarily simple roots, and you can kind of construct their negatives as well using the braid group action. And they show that the P center is essentially polynomial in those generators.
Great.
Right, and this is recorded in this in the last page that the spectrum of the P center is essentially functions on an open Brio cell.
Great. Yeah. And sorry, actually, so for Z0 intersect Z1, is there any, in terms of that picture over the Bruhat cell, is there something simple you can say or no?
It's kind of it's a guy which will be given by Chevalier's theorem essentially. I mean, if you ignore this, then kind of so what's the Harish-Chandra center? It's a functions on the open Brio cell which are invariant on the adjoint orbits. Does it make sense?
Great. You're saying they just pull those back to the cover, and that's the.
Yes, because the Harish-Chandra center only involves the even part.
Great.
So,
Okay.
so maybe you don't pull. Yes, you pull them to the cover. Yeah, in this language, I think.
Okay. Thanks very much.
Okay, so let's start looking. We have a little bit of time, so let's start. Maybe we can try and get to this state one more theorem before we finish. So let's start talking about Lustix form. So this is an appreciably more difficult form of the quantum group. So this is the A subalgebra. Of UK generated by these elements. So with alpha and pi and S and Z. So these are exactly what we've seen before, right? So these are the divided powers. Right, so this is really an analogy, exact analogy with what we've seen for algebraic groups. Okay, and then UA plus is right. This is generated by E alpha S and so on. Okay,
So
just
here,
the
strictly
UA
speaking,
plus.
We are talking about the simply connected form.
We are always talking about the simply connected form.
Yeah.
I'm never not talking about the simply connected form. Let's just say this. So UA plus and UA minus generated by the divided powers for the positive and negative part. Okay, so the first thing we want to talk about for Lustix form is a basis. Okay, so if we take a root alpha and integers then let's just recall that we have this this element, this kind of quantum binomial coefficient. So I'm writing it like this, but really I could write it in a way that made it look more like quantum binomial coefficients. Okay, so this is, in terms of the distribution algebra, this is really playing the role of the binomial coefficients you see there in the toral part of the distribution algebra. Okay, so we're going to follow Calder's talks. So let's fix a reduced expression of the longest element. Okay, so remember, we can basically reconstruct all positive roots from the longest element from this reduced expression. And I'm going to define the divided powers in general by using this action of the braid group.
Well, it's still going to be the divided powers of,
Yes, yes, they're still divided powers of something. Right, so just recall now that when we do this, the advantage of picking, one advantage of constructing things in this way by this reduced expression is that we now have that the positive roots are a totally ordered set. Okay, so let's just end with this. So pick a reduced expression of the longest element. Then this algebra has an A basis given by terms of the following form. Okay, so when I look at these terms, I'm going to go through the ordering in the positive roots in one direction, and then I'm going to go in the opposite ordering for the negative roots. right, and I should have nj, mj, t alpha greater than or equal to 0, and delta alpha in 0, 1. And let's just say that UA plus is spanned over A by the terms of the form of the EJ terms, and UA minus is spanned by these terms. So this basically looks very similar to what we had for the distribution algebra case. Okay, there's one thing that maybe looks somewhat unfamiliar, is that if we were trying to think about the triangular decomposition for this algebra, maybe for the UA0 part, you might just want to say, okay, let's just take the subalgebra generated by K alpha plus minus 1. But actually, that's not what you want to do for the UA0 part. So in general, you're going to need to include generators of this form to get the UA to get the kind of toral part of your in your triangular decomposition.
But that's
Okay,
exactly
but-
what we've seen for the distribution algebra.
And also what we've seen for the distribution algebra, yes.
We haven't seen this K alpha to degree 0 or 1, but that's again, this is the part of the same 2 to power rank G unlength.
Yes, yes. So maybe I'll just end with a very quick remark about the proof of this. So actually, so in Lustig's original papers, what he does is he proves this for one special choice of reduced expression for W0. So he kind of he picks a nice reduced expression with certain properties and then proves it for that reduced expression. And then an argument by Dyer and Lustig shows that once you know it's true for one reduced expression, it's true for all reduced expressions by using the action of the braid group. But in his book, I think Lustig essentially manages to do away with all of this, and it's kind of much cleaner. And he really just gives a proof using starting with any choice of reduced expression. But his book is maybe also not so easy to read. But yes, so I just wanted to make this remark if you do look at his papers. But okay, I'll stop there and we'll do more next time.
All right, let's thank Jay for the talk. Questions?
Jay, I have a question. So U sub A we took as generated by divided powers in E's and F's, and then just the K alpha plus or minus 1s. So how do we?
Sorry, it's just the divided powers for so these guys are just like this is just divided powers of E's and this is just divided powers of F's.
So it says the line above that, it says this is the A sub algebra generated by.
Oh, so the whole algebra is generated by all of these terms, yes. But the positive part is just generated by the E's, and the negative part is just generated by the F's.
And so we can get the K alpha AN, like these kind of the divided power of the K's, sort of, right? Like how do we obtain those?
Yeah, so we'll kind of. Oh, sorry, no, go on, please.
Jay? Yes,
No, I don't want to answer.
All right. So since you are doing simply connected version, this binomial coefficients will be obtained by taking commutators of E's and E alpha to S and F alpha to S.
Okay.
And that's also the case for characteristic P.
Mm-hmm.
So maybe you see this also, I mean, in the theorem that Ivan stated as well about dis G modules versus G modules. And there's this assumption about it being simply connected. And sort of the point there is that you can always recover the torus bit from the root subgroups or the root group parts. And so when you're in this simply, that's why simply connected often is kind of like great, because your toral bit is just kind of already coming from the other part, from the nilpotent part.
Right. So if you were to deal with non-simply connected groups, then you will need to include binomial coefficients for what is missing for what is not present in the root lattice.
Thank you.
More questions? All right, let's then declare that we are done for today, and the next meeting is in a week.